All right, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. Here we're starting with sets and Venn diagrams, and we were just getting into the Venn diagram at the end of the last video. So reiterate here, we got our universal set that's going to be everything we're interested in and whatever typical problem we're on. And we draw that in a rectangle and a circle for each set involved. In this case, there's two sets, A and B. All right. And this is, looks like, and let's just see a situation. Let's say our universal set is the integers from 1 to 10, okay? And say A equals 1, 2, 4, and say B equals 3, 4, up to, I don't know why I should just put 3 in there, 1, 2, 3, 4, 3, 4, 5, 6, say. Okay, so in our picture is what this would look like, where each of these elements live. Remember, they all live within the rectangle. Well, all live within the rectangle. Because that's our universal set. But we want to think about the regions. So let's see here. The numbers 1, 2, 3, and 4, they're all in A. Okay? However, I'm going to write it as 1 and 2 out here, 3 and 4 because they're in both A and B. And then what's left in B is 5, 6, and then out in the we got 7, 8, 9, 10 living outside of both those things. You want to think about how that may be visualized with a Venn diagram. And Venn diagrams seem really kind of simple and maybe useless, but they are actually very useful tools. The whole idea here is you're creating a schematic for a higher level of thinking, right? You don't have to write. You're writing down only what you need, and it becomes a simple drawing then. But then you could draw conclusions from that. Okay, we have some operations on sets. Between two sets, okay, we have one of them is the union. The union of A and B, which is written as A union B. I don't know what you want to call it. That is not a U. I call it big cup, but that's because that's what it is in LaTeX. It's union. You really call it union. And it's a set of elements that belong to A or B or both. I'm not going to continue saying or both for the rest of the year. Whenever I say A or B, I mean or both. That's generally what we mean by that. If you mean A or B, but not both, that's something else. That's called the XNOR. Don't worry about it. We don't cover it in this class. It's more a computer science thing. So, but here, our union, it's A or B or both. Okay? So, what does that look like in a Venn diagram? It's this shaded region, right? A or B, right? So, for instance, if A equals 1, 2, 3, B equals 2, 4, 6, A union B is 1, 2, 3, 4, 6, or the set containing 1, 2, 3, 4, 6. I guess the big thing to notice, unions are generally easier than the next one that we learn, because since it's in both of them, we could simply write down all the things in set A, and then all the things in set B that were not in A. That's a fairly easy to list that thing. And I also want to say union generally grows. Okay, it definitely doesn't shrink, and it usually grows. The union of two sets generally is a bigger thing, as you can see, right? The red area is bigger than any of the one circles. Then we have the intersection of A and B, and written as A intersect B, and it's the set of all elements common to both A and B. By the way, one of the ways I used to distinguish these when I was learning is and. This one is closer to looking like an A, the intersection sign. I don't know if that works for you, but that's how I kept it in my head. So A intersect B is the set of all elements that are in A and they are in B. So our intersection is going to be the little red area where they overlap, right? That's a picture of A intersect B. And if A equals 1, 2, 3, the set containing 1, 2, 3, 4, B containing the set containing 2, 4, 6, think about what A intersect B is. So here it has to be in both. Hit pause, think about it. Okay, well, let's see here. We got 1 is not in B, so that's not in there. 2 is in A, 2 is in B, so that's in the intersection. 4 is in A, or 3 is in A, but it's not in B, so that's not in there. And then 4 is in A, and it's in B, so that is in there. 2, 4. And that idea is that generally the intersection, it shrinks. Notice that it's smaller than A or B, right? It's getting smaller. It doesn't get bigger. It definitely doesn't get bigger, but it usually gets smaller. Those are two things. That's how we think of intersection. If A and B are sets, they have no elements in common. That means that their intersection is empty, right? A intersect B is the empty set. We say that A and B are disjoint, and kind of boring. Here's the picture. The complement of a set. Here we need the idea of a universal set to have a complement. Notice union, intersection, we don't need the idea of an universal set. But if U is a universal set and A is a subset of U, okay, then the set of all elements of U that are not in A is called the complement of A and denoted, well, A with the apostrophe, and we call that complement. Some people call it, put a C up there, and sometimes people just put a line over the top, just in case you see it from another book that way. Okay. All elements in U, and they are not in A. All right. This is what it looks like. Everything in U that's not in A. That's A complement. So if U is the integers 1 to 10 and A is the set of integers 1 to 3, then A complement has to be everything outside of that, A, 4, 5, all the way up to 10. Okay. Now, properties of set complements is if U is the universal set of A and A is a subset of U, just their setup, the complement of U is the empty set. The complement of everything is the empty set. The complement of the empty set is U. The complement of A complement, you're back to A itself, which would, I advise you, I would think about these things, make sure they make sense to you. These are not really needing to memorize, more understand. And A union A complement equals the whole universal set. And the intersection of A and A complement is empty. In other words, A and A complement are disjoint sets. Some properties of set operations. Commutative law for union. A union B equals B union A. Same for the intersection. All right. Associative law. All this means is we could do, if we have A union B union C, we could do A union B first or B union C first. It's just like 2 times 3 times 4 or times 5, right? We could write that. We could do 2 times 15, or we could do 6 times 5. Those are all equal. That's just that idea there. There's a same associative law for intersection. Distributive law for union. This is pretty useful. A union, then B intersects C in parentheses. Just like distributive law, let's say 5 times let me do it this way. 5 times x plus y equals 5 times x plus 5 times y times. That's just like this. A union B intersects C. So you could do A union B intersect A union C. That's distributive law. Similarly, we have one for intersection. Okay, and these are all listed in your book and in the slides if you look at them from the old section. Now, let's think about this. Which of the following sets correspond to the shaded region of this Venn diagram? Now you got to try some things out here. And I'm going to let you think about that. Maybe hit pause. And it's the intersection of all three. A intersect B intersect C. All right? That means it's in A, and it's in B, and it's in C. And hopefully we can see that in our picture. How about this one? Go ahead and hit pause for a second. And think about that. A union B intersects C. Okay. Let's see, how do we get that? We could think about that as, so let's see here. The green, we'll do A union B. We'll do A union B in the green. That's pretty. A union B, right? And we got that straight from our slide. Everything in A or B. So that whole green area is A. We'll do that in green. And then, let's see, in yellow, we'll do C. All right? C is all in yellow. And their intersection, so since we're taking the intersection of the green and the yellow, or A union B and C, is it's going to be where it's both green and yellow. And in this case, we see that that is exactly the region, that red region. See that? The red region is yellow. And that's how we could figure out these types of problems. This is also an interesting law, and it becomes very useful in probability, so I will bring it up again. But notice A union B quantity, meaning the whole thing in parentheses, complement, is you take A complement, the sign flips to intersection, and then B complement. And the complement of A intersect B is A complement union B complement. What I would like for you to do is draw Venn diagrams, okay, to see that these are actually true. Maybe I'll do the first one. A union B complement, okay. Well, we have our Venn diagram. We have A and we got B. Well, we know where A union B is. Let's see here. That's everything in the red, in the A circle or the B circle. So the complement of that is everything outside of it. We'll do the complement in red. So we did this whole side in red. You could piece that together even more if you wanted. I skipped a little bit of the shading in the A union B for the sake of brevity. Now, we want to see us get the same, we should get that same red area. So let's see. Over here in green, I'm going to do A complement. So A complement is green. B complement I'll do in yellow. Okay. And of course, when I look at the intersection of green and yellow, I get the red area. So that means that A union B complement equals A complement intersect B complement. I would like you to do the same for this one. It's a good practice with the Venn diagrams. All right. Have a great day. Let me know if you have any questions. We'll see you next time.